Let us now consider ionic reactions. In particular, we want to consider molecular equations, total ionic equations, and then net ionic equations. So first of all, let's look at the reaction of two ionic materials, magnesium chloride and silver nitrate. We know these are ionic materials because of our general rule. Each are metals and nonmetal, and this is a metal and a nonmetal. And so that is the indication we have two ionic compounds that we're going to react. A very typical reaction that ionic materials undergo when you have two of them is called a double displacement. That is where the cation of one molecule interacts with the anion of a second, and the cation of the second interacts with the anion of the first. And so if we're going to predict what products we will get, there is a three-step process that I recommend that you go through. The first is to pair one cation species with exactly one anion species. A pair does two make. So the first thing I'm going to put here as a reminder is pair. And so you can see the pairs. I have one magnesium, and I'm going to pair that with one nitrate. At this point, I don't care whether the compound is charge neutral, and I don't care whether the equation is balanced. That will come later. The second pairing that I'm going to do is to pair one silver, and here's where the foot fault usually occurs, with one chloride, not two, so this would be AgCl. One silver ion and one chloride anion. I'm not going to pair it with AgCl2 because that would mean I have 1, 2, 3 ions, and that is not a pair. So let me take that 2 off. Okay, and with that, we now have what's called the molecular equation because each compound here is written as a molecule. Oh, before I do that, let me make sure everything's charge neutral first of all. So let's see, the charge on a magnesium is +2. Oh, this is -1. So this is not a charge neutral species. I'm going to cross multiply. I can see that I'm going to need 2 nitrate groups there. So let me go ahead and take those off, and let's balance this. There, that is now charge neutral. And how about this material here? Silver is +1, chloride is -1, and so that is now charge neutral. So the second step is therefore, once you pair the materials, the second one is you make sure that each pairing that you've had is charge neutral. And only now are you ready to do the third step, which is balance the chemical equation. And these are very, very easy to balance when you have ionic equations because every one of these is necessarily paired. And what I recommend you do is quite simply just pick whichever chemical species has the largest subscript and start with that. And the largest subscript I see is a 2 for that and a 2 for that. That is not a 3, remember, that's one nitrate group. So the largest one I see is 2, so I know I need 2 chlorides. Therefore, if I need 2 chlorides, I'm going to have to put a 2 there. 2 chlorides means I need 2 silvers. I'll put a 2 there. 2 silvers means I need 2 nitrates. I have 2 nitrates. 2 nitrates means I need 1 magnesium, and I have 1 magnesium. So everything is balanced in this equation. I now have completed what is called the molecular equation. So when you balance a chemical equation like this, you necessarily get the molecular equation. Well, if you put these chemical species into water, you're going to find that some of these actually break apart into ions. And so there we need what is called the total ionic equation. And you do that merely by breaking everything down into ions that comes apart, if you will, in solution. So magnesium chloride does. And by the way, you get that information from a solubility table. So for now, you will have to trust me because you do not have a solubility table in front of you, but magnesium chloride indeed will break down into 1 magnesium and 2 chloride ions. So let me show you what that would probably look like. If you have a container and it has water in it, and you take some magnesium chloride, and let's say this is a solid material, and you spoon some out and you put it in water, you're going to find that it breaks apart into magnesium 2+ and 2 chloride ions. And this is what we're trying to depict here, from going from the molecular to the ionic. Right. The same thing will happen with our 2 silvers, 2 silver nitrates. You're going to get 2 of those, 2 silver ions, and you're going to get 2 nitrate ions. And the magnesium nitrate, this species here, will also break apart to give you 1 magnesium and 2 nitrates. And finally, the last chemical species does not break apart. If you look on a solubility table, you will see that silver chloride is indeed precipitates from an aqueous solution. And so we draw an S there, meaning solid. Now we have the total ionic. So let me write some of these other chemical species here. We have 2 of these, 2 of these, 2 silvers. Let's go ahead and add a couple of silvers here. And let's add a couple of nitrates. It's getting kind of busy. So this drawing here is the schematic for this material here. Let me clean this up. Now that we've already put everything in the reaction, there's our solution. What the product side of the equation is trying to get across, the product side, is what happens to these materials after they're all mixed together. So if you will, you can almost think of this as a before and an after. So what happens here? What does this mean? When the magnesiums and nitrates come together, this tells us that they break back apart. But look at what happens with silver chloride. When the silver chloride comes together, it stays together. What that would mean is when 1 silver bumps into a chloride, these ions now go away and it becomes 1 single species, AgCl. And the same thing with this silver and this chloride. They become AgCl. And this is your new solution. Free-floating magnesium, free-floating nitrate, and silver chloride particles. So, the last equation that is of interest is what would be called the net ionic. And net ionic is where these ions that don't change from the reactant side to the product side, the so-called spectator ions, because they're really just watching other things react. They're just spectators. They're not really participants. And so the net ionic just involves the things that actually change in going from the reactant side to the product side. And so the easiest way to do that is merely to cross off all spectator ions. I'll cross off magnesium. Why? Because magnesium is a free-floating ion on the reactant side, and it is a free-floating ion on the product side. I'm not going to cross off chlorine because it's a free-floating chloride ion on the reactant side, but it is totally different. It is part of a compound on the product side, so it's actually changed. The same with silver. Here, silver is an ion, and here it is part of a compound. And finally, the nitrate is going to cross off because it is exactly the same on both sides of the equation. It's a free-floating ion here and a free-floating ion here. So what is left makes up what is called the net ionic equation. And so what we really see, the bottom line, if you will, it's an accountant's bottom line, is two chlorides combine with, and we saw that here, two chlorides combine with two silver ions to give you two silver chloride molecules. And there you have it. That's the process I would recommend. If you're given a formula and you need to do two things, predict the product and then declare what your total and net ionic, a good process to go through is this. To predict the product, you pair ions, you make each of the resulting chemical species charge neutral, and then you balance the chemical equation. That necessarily gives you what is called the molecular equation. From that, you break it apart using a solubility table to determine the total ionic equation. And from that, you cross off your spectator ions, and that will give you the net ionic equation.